Sorry about the delay. I just had to finish flipping those pages. So okay, let's go ahead. Let's start with 4.1 number 2, and we'll go from there. So 4.1 number 2, we're doing barium hydroxide, memory serves, in aqueous state plus HCl in aqueous state. And we are looking at how this goes. This is going to form barium chloride and H2O. And if I leave it in this way, there's several different ways to write this down, but if I do it, that looks like a Z instead of a 2. If I do it for, if I do it this way, I've got my 2-to-1 ratio. I've got some moles of barium hydroxide. I've got some moles of hydrochloric acid. This problem is set up so that the hydrochloric acid is excess. How many moles of barium? You got the moles handy for us?
Yeah, there's 0.0057 moles of barium hydroxide and 0.0138 moles of HCl.
I'm going to switch to millimoles because 5.7 and 13.8 is easier for me. So I just took your numbers, divided by 1,000 to get it into millimoles. HCl is excess. I had to pause to think about that because I can't just go with smaller number. Is limiting because we've got that 2-to-1 ratio. But if this is my start point, I did a little bit of mental math, and I said, we're going to have minus 5.7 times a 1-to-1. I'm going to have minus 5.7. Coefficient of the limiting reactants on bottom. Coefficient of the thing we're looking at is on top. I don't really care about the products in this case. Let's think about it, right? We'll think about it. Plus 5.7 times 1-to-1, 1 for the barium chloride, 1 for barium hydroxide. That's going to be 13.8 minus 10, 11.4. That's going to leave us with 2.4 millimoles. Is that right?
Yeah.
Or 0.0024? What number did you get?
Sorry, this is for the excess.
The excess HCl.
I got 0.231 moles. So
0 point?
She's not working in millimoles, so maybe it's...
No, but that's what I was expecting to do 0.0023.
Sorry, that was the molarity.
Okay, then we're probably in the same ballpark.
Yeah, sorry.
It's okay. I just wanted to make sure that we're on the same track, and I think everyone has the same numbers for this one.
No.
Oh, no, okay. Let me look real quick. Let's see here.
I did it differently, so I split it up into that, and then I found moles of OH and then moles of H+, and then, so that's technically the HCl.
No, that's fine, that's fine. Where did you do your chemical reaction? I mean, but your moles of HCl were decreased. Did I write something down wrong? That's 5.7. Where's your moles of OH minus? Or your moles of barium hydroxide?
How do you do the mole ratio again? What's on the top and what's on the bottom?
And then where's your moles of
The
HCl?
denominator is the end here.
Okay.
And then the top part
Make it
is
6.
Is the
Oh, I
one
took
on
up the 6 this way.
Okay.
And then
So
you
like
subtracted the 2
this
from each other?
minus that.
Yeah.
Yeah.
Where's that?
Or no, this minus this. Because that's the moles of OH.
Right, because you multiplied by 2.
Yeah.
Yeah.
And then I converted these into molarity first, and that's where I got this to get the moles.
Ooh, you have to be careful. So you subtracted your molarities.
Yeah.
Now, that's going to be okay in this case, because everything's in the same total volume. But you have to be really careful about that in the future.
Okay.
It's best to do all of your subtractions and your manipulations in moles, and then switch it to molarity at the end.
Okay.
But that means I'll go ahead and check this. What was our total volume then?
It was 0.05993 liters. So 59.93 milliliters.
Okay. So I'm going to go ahead and do 2.4 divided by 59.93. And you get something like 0.4 molarity, something close to that. Oh, I should be more careful. Well, just in terms of usually I do the problem a little bit slower. I was trying to go really fast, and so I didn't get the numbers that are given in the problem. I was just kind of grabbing the numbers that I was, provided partway through the problem, and that just gives a lot of opportunity for us to not be talking about the same thing because we might be jumping into different spots of the problem. And now I'm like, oh, how much do I want to rewind? I'm calculating molarity of 2.4 divided by 59.9. I'm getting 0.04 molarity, which give me a pH of like 1.4.
Yeah,
Okay.
that's what I got. I'm just lost about like where you're getting your numbers.
Where'd you get your concentration? Oh, you got 0.039. You had 0.039. I just am off by a little bit of rounding. I got 0.04. So we're totally on the same page. We're doing the same thing. I just got worried for a second. Okay. So the types of questions that were coming up before I started recording, what were we asking about?
It was a question where it asks about like the chemical species predominant.
Dominating chemical species, right? So when we look at this, when we're talking about pH, we can say, well, look, HCl is in excess, so why don't I say HCl is dominating the pH?
Yeah.
But the important thing about HCl is that if I put HCl in water, it goes through, I'm not even going to put the double arrow because it's a strong acid, it goes to H3O plus Cl minus, right? And it turns out the thing that's dominating the pH is that excess H3O plus that's in solution.
Okay. So since it's a strong acid, it turns into H3O plus, and they're like, okay, that makes sense. If it was, what would you say if it was like a weak acid?
If it was a weak acid, well, it depends on which point in the weak acid we are. If we're at the initial point, it's just the weak acid.
Okay.
If we're at the equivalence point, it's just the conjugate base.
Okay.
If we're somewhere in the buffer range, you're going to have two things because it's the two things in, right? The buffer range is where we have that weak conjugate system. Okay. So we need the weak acid and the conjugate base. And I think you'll notice one of these later problems has two boxes for it because there's two species that are both playing a role. You could always argue one is more than the other because you're either before the midpoint or after the midpoint, but you need both of them. Are there other questions about number 2 before we go on to those other things? Okay, so that's number 2. Did that get to your question? I don't even know if I addressed your question. It looks like you did great.
Yeah, I got the answer, but
yeah, so conceptually, okay, so I remember now. So conceptually, the big problem here is why didn't I have to do an equilibrium? What's going on with that? And that is because, again, this type of idea of the HCl, normally what we've seen in class the last few days is we've done some chemical reaction with base, and then we do an equilibrium afterwards because we've got a weak acid conjugate base system. Here, after I do my chemical reaction, sure, I've got barium chloride floating around in solution, but barium ions and chloride ions just don't really have any equilibrium for forming barium hydroxide or hydrochloric acid. And so the question becomes, well, why not? Well, if you had hydrochloric acid form, if Cl minus took H plus from water, acted as a proton acceptor, you form HCl. What does HCl immediately do? It just immediately disassociates. So we have that situation where that's not going to be an equilibrium. Right? That's just going to be all the way towards products or reactants. It's just going to be completely to one side. There's no measurable equilibrium. Turns out barium forming barium hydroxide, same situation. It's just too soluble. It's a strong base. It just redisassociates. It doesn't really form. So there's no measurable equilibrium in these situations at low concentration. Of course, if I wouldn't do this to you, but I want you to be aware, these things get a bit more complicated if you go to really high concentrations where essentially we can act like the H pluses and the Cl minuses aren't interacting with each other at low concentration. A high concentration, you have to start dealing with that.
That's like, we say sodium chloride dissolves in water, but it stops at some point because the ions start to interact with each other. And that's where you get into like high concentration situations. And we're going to avoid those all quarter. Because I don't want to do activity coefficients. It's a weird equation. I mean, I do, but I would need to brush up on it, and it's just not necessary for what we're doing. Just like in 127, it wasn't necessary to do the equilibrium table for what we were doing. It was like, look, just doing stoichiometry is enough in this class. Here, I'm just trying to warn you, like, hey, right now, fully dissociates is enough in this class. Could it get more complicated? Yes. I'll tell a story in class at some point. I have a friend who works for a pharmaceutical chemical company. They get hired to make these like custom solutions. And it was like 5-6 years ago. She called me and she was like, hey, I've got to make this buffer. I'm supposed to make like 200 liters of it. It's like, tons and tons and tons. And she's like, we're doing a test batch of like 1 liter and it's not coming out to the correct pH. And I had her send me her stuff and I was like, oh, it was a really high concentration buffer. And I was like, at this concentration, like, you can't just mix things together like it's low concentration. Your approximations all fail. And so you have to, the nice thing is it turns out that there's like an online solver for like, hey, activity coefficient solver. And so she was able to get it to work. But it was like one of those things where it was like a really high concentration situation. It's like once every 15 years, somebody's like, hey, why isn't this working? It's like, oh, high concentration. So someday in your future, maybe, but not in this class. So because we're doing a low concentration, strong system, there's just no equilibrium to worry about.
So is that green formula like a hypothetical thing, or does that actually happen after that reaction takes place?
After that reaction takes place, that HCl that's left in solution will fully disassociate.
Okay.
Technically, you could say even before the chemical reaction, that's how it already existed in solution. Right? When I say HCl aqueous, I really mean H3O plus aqueous plus Cl minus aqueous.
Even the barium hydroxide.
Even the barium hydroxide, which was the solution Dr. Retzek sent you, was doing the disassociation before the reaction.
Yeah, for some reason that made total sense to me.
It makes sense.
Yeah.
It totally works. Like, both of those ways make sense. That was a different thing. But there's multiple ways to solve this problem, is what I'm getting at.
So if it was a strong acid with a weak base, would HCl not react the same way?
So HCl is the strong acid?
Yeah, and then there's...
And then let's do ammonia as the weak base. In that situation, is HCl still excess?
Yeah.
If HCl is still excess, this is still going to be approximately the same solution. We could technically do an equilibrium step for the conjugate acid that's reacting. That's going through some equilibrium, because we'll make a weak conjugate acid that should disassociate and put extra H plus into solution, right? We will find the extra H plus that it puts into solution is just way less than what, like, is going to put like 1 times 10 to the minus 7 moles of H plus into solution. It's just going to be way less than the HCl is doing. So what I mean is, or to think about it, let's not do that yet. Let's leave that there. And I'll come back to it after we do a weak acid, strong base situation. Because we can do it on our titration curves and talk about it there.
Like number 7.
Did you say like number 7?
Yeah, I was wondering if that's the situation.
What's number 7? Okay, so we good on number 2?
7 is all of the curves.
Okay, all of the curves. So this is a general understanding idea. And I think, again, I'm a little bit of a jerk. And I think we really covered the stuff to do this today. So the question is asking us, this is number 7. You're following along at home, I'm sure. There you go. Okay. So this is asking us which corresponds to the highest number of moles. So that is which one's equivalence point is furthest to the right. Right? So the stoichiometry we're going to learn today is just which one takes the most base is going to be the highest number of moles. Actually, I have to be careful for a moment.
Yeah, so I think it's number 1.
So the most base, like farthest to the right.
Right, and we've got a concentration of our base, so yeah, that's going to be number of moles. Well, hold on, let me check something.
I think that's right.
Okay, yeah, that's going to be highest number of moles.
Could you do a tiny little sketch
Yeah,
so
yeah,
we
yeah.
can follow along?
So if we are doing, so we're looking at a couple curves, and I'll just do 2 curves, right? We've got one curve that's like that, versus one curve that's like that. Right, now if these were on the same scale where this is like 25 milliliters, and then over here is 25 milliliters, right? This one's down lower. Remember, x-axis is the stoichiometry. We learned that today. So this one takes more moles to get to the equivalence point. This one takes less moles to get to the equivalence point. So this one would have more moles of analyte present. That's how we think about number A. Number A. Part A. Part B asks,
Which curve corresponds to the highest concentration of analyte?
oh,
The highest concentration of analyte would be the lowest pH?
no, it should be the one that is the highest volume of base if all of our samples are the same volume. Are all of our samples the same volume?
Oh, the correct answer is cannot determine.
So if our samples are different volumes, we can't really tell which one is highest concentration. We can just remember the equivalence point just tells us moles are equal to moles. So it tells us about moles. It doesn't tell us about concentration.
It doesn't tell us about volume. That's like,
It doesn't tell us about
that's why we
volume.
can't.
So we can't, right? Remember the thing we did in class today was like the molarity of weak acid times the volume of weak acid is equal to the moles of weak acid. If we don't know the volume of weak acid, we can't say what the molarity is. We can say the moles because the moles is what we're reacting with. But unless something tells us the volume, we're kind of the volume of our analyte, we're kind of stuck. Now, if you run the assumption, this is not a safe assumption to make, if you run the assumption that all the samples are the same volume, the one with the most moles is the highest concentration. But that's an assumption. Hey, come on in. Which class?
4 to 6, so Monday, Wednesday.
Yeah, 124. Okay.
Yeah.
This is mostly 129, folks, so I'll help
Okay.
you out in just a
Yeah.
sec.
So there are four, so I understand how you're comparing those two because you're looking
Mhm.
at that one point on the curve at that one
Yeah.
spot. But there are four different curves.
Uh-huh.
So when it says which curve corresponds to the sample with the highest moles of analyte,
Uh-huh.
or at what point? The point that it's pointing to? Or?
The first, no, just each curve, right? The point that it's pointing to, I think it's just pointing to which curve is which number.
Yeah.
That has to
These
do
two
with
have
E and F.
like an indicated spot in blue.
I think that's for a later problem.
That's the one where.
I think,
Oh.
Yeah, that's for part E and F.
Okay.
It's for part E and F.
Okay.
Okay. What's part C?
Which curve corresponds to the strongest base?
Strongest base?
Yeah.
Okay. So, these are, so do you think a base is going to start with a low pH or a high pH? So which curves start with a high pH?
4.
Is it the answer 4?
Yeah.
Okay, cool. Whew.
And then
This is hard to do when I'm not looking directly at the curves.
If you,
Okay.
No, this is more fun.
Okay. And then strongest acid was the same problem though. That's the lowest pH. The next
Yeah.
one asks
The lowest pH at the,
at the beginning.
Like a lowest.
or the, so there's a better place to look than the beginning for figuring out which acid is the strongest. It's not the pH at the pH at the beginning corresponds to it. What'd you say?
the equivalence?
Oh, better than the equivalence point. The other point? The midpoint. Right, because at the midpoint the pH is the pKa, and the pKa is how strong the acid is. So if we look, so I tried to do it with these two, but then I drew it crooked. This one has a higher pH at the midpoint. This one has a lower pH at the midpoint. So this one with the higher pH would be a weaker acid. This one with the lower pH would be a stronger acid. But then I didn't draw it straight, so it's hard to do the comparison.
Can I show you something?
Sure.
Curve number 2 is weirding me out because it's got those 2 little
Yeah.
plateaus.
Polyprotic.
Yeah, I don't understand what the multiple curves.
So if we look at something with one proton to react, we see a curve like this or this. If we see something that has 2 protons that can react, we end up seeing 2 bumps.
Okay.
If you see a curve with, if you have an acid with 3 protons to react, 3 bumps. Yeah. Right, and so it's like reacting away. So like, for example, someone asked for me to do a polyprotic, and I was like, oh yeah, we'll probably get to that on Wednesday. I didn't realize it was on this 4.1. That's my bad. So this, if I cover up this chunk, so like if I cover up this bit, it just looks like a titration curve, right? Like there's your titration curve reacting with 1 proton. If I cover up this bit, it looks like a titration curve of 1 proton. So this would be like looking at H2CO3 going to HCO3 minus. Would be looking like from here. And then higher up here, this would be looking at HCO3 minus going to CO3 2 minus. That would be like looking through here. Yeah?
Can you do E?
What is E?
E asks on curve 1, which is shaped like your curve 1, at the point indicated, which is the equivalence point,
Mm-hmm.
I think. Yep. What's the predominant chemical species in solution that will determine the pH?
Ooh. So, what'd you put?
I put H2O.
Ooh, yes, by. Do you remember the last problem we did in class today?
Yeah.
And I did it kind of in the last 10 minutes. Which equilibrium did we have to do to determine the pH?
Say that
It was
again.
like we had to find POH and then to get the pH.
Very last problem I
We
did,
did.
right?
Yeah.
Right, because all that was left was the acetate anion. Right, and so I had to do the equilibrium of the acetate anion at that point. So it wasn't just water, because if it was just water, it would be 7, like we saw for number 4 or number 3 that we didn't do today. But if we are looking at the equivalence point for a weak acid titration, it's going to be the conjugate base that's going to be predominant. Did they tell us what acid it is?
It just said assume that the analyte is a weak acid or base. It didn't tell us what it is.
So just A minus, I
That's
guess.
the answer for E.
Could
Just
you
a
say that
just
one
a generic A minus.
Wait, so could you repeat what you just said one more time about
Yeah,
weeks?
So if we are at the equivalence point, we've added enough strong base to completely react away all of our weak acid and convert it to conjugate base. That means in solution, all we have is conjugate base interacting with water. And the conjugate base equilibrium is what will dominate and determine the pH.
At the equivalence point, we've completely reacted all the weak acid with our strong base. So at the equivalence point, all we have left in solution is the conjugate base
Yes.
of the weak acid.
Yes.
And the conjugate base of the weak acid, the anion, will determine the pH.
Uh-huh. Because the anion acts like a weak base.
Could you like talk through that for F on the same problem?
F is a curve like this.
Yes.
Yeah.
F is
Oh.
And the
polyprotic.
point indicated is.
In the buffer range. That one, don't worry about that one.
it's not a graded question, right? It's just like,
No,
we'll
it's-
still go over it. We'll still go over it, but like,
Later.
I feel like this is like, oof, we're doing it tomorrow, we're doing it Wednesday in class, right? So, we're at this point where we're in a buffer range for a polyprotic system. So, the way I would write this down, so I would write it, so like, we're in this area where I'm gonna have a weak acid with its conjugate base, but it's gonna be like an HA minus and an A2 minus. We're gonna have two things present when we're in the buffer range. If I wanted to do it for this lower part of the curve, I'd have H2A and HA minus. Because I have two things present. And whenever we look in a buffer range, we should always have two things that make a conjugate pair. So in this lower part of the curve for a diprotic, there's just two protons. It's H2A to HA minus in that first buffer range. And then for the second buffer range, it's just the second proton falling off. Ooh, tricky question. What's the pH at the first midpoint
The PK.
of the first
Yeah,
proton? What's the pH at the second midpoint?
The second proton, the PK.
Yeah. Yeah.
So but it doesn't tell us what we're working with.
Right, so just use the generic HA minus, A2 minus.
So when it says what's the predominant species that determines pH, at that
Mhm.
point, that's the midpoint of the second proton.
Uh-huh. It should say, I think I've got to add a note that says use the generic
Yeah,
HA, H2A,
okay.
A minus.
So then on the second, this question would be HA is determining it, not A?
Both together. So if you notice, this is part F.
Mm-hmm,
There are two spots for F
mm-hmm.
because there's two compounds you need to input for F.
Oh, that's really confusing.
There's not a great way to structure those things. There's just too much. This is where like, I either need to get better at writing questions or we just need to do more paper exams.
So the first chemical species is A2 minus, and then the second would be HA minus?
Yeah.
Okay.
And I don't know if order matters.
You said A2 minus?
A2 minus.
Yeah.
And then the second one is HA minus. Oh, yeah, that's right.
I looked everything up, but I forgot to read what
Wait, can you go over E again?
Oh, 2 minutes.
E again.
Yeah.
Okay, so on curve 1 at the indicated point, which is the equivalence point, what is the dominant species to determine pH? So at that point, at the equivalence point, all of our weak acid is reacted. All of our weak acid has become conjugate base. All of our strong base has been reacted. All of our strong base has become water, essentially, by reacting with the weak acid. The only thing left in solution is our conjugate base, A minus, and water. So the equilibrium we look at to determine the pH is going to be that conjugate base in water. So that conjugate base becomes the thing that dominates the determination of pH.
I'm still confused on that, because wouldn't we have excess strong base if there's?
If you're exactly at the equivalence point, no.
There's no excess of either of the
Correct.
acid.
Weak acid is totally gone, strong base is totally gone. Now, you could argue with me about like how likely is it that you get exactly to the equivalence point, right? But as long as we're close enough, we can say approximately. If you go a little bit past the equivalence point, yeah, then you've got excess base, right? Even a little bit past, you've got excess base. But we're going to be approximately at the equivalence point, so the strong base is approximately 0. The weak acid is approximately 0. It's just the conjugate base that's present. Let me answer some 124 questions. You all start working on number 9 together. That's the next one. And it looks like it's a weak acid titration problem. So start working on number 9 together, and I'll be right back.
Okay, so looking at number 9 now, people have been working on it, we're doing pretty well. We're down at part D, and is it part C or part D?
Hang on, it is part D, sorry.
Part D. And we have a lot of people kind of having the same mistake. So what's happening here is we've got a base. It turns out that this nitrogen can behave like a base. This nitrogen can accept another proton. So that's going to have that lone pair on there is going to make it a proton acceptor. We're going to add, I'm just going to put it as H3O+. I know it's HBr, but I just care about the H+ from the HBr. And that's going to get us HONH3+ plus H2O. Okay, so that's going to be the chemical reaction step.
Hang on, that confused the heck out of me.
Yeah, we are. I'm also.
Could you write it with
confused.
the BR just so I can see where we are? HBr.
Right, this is our chemical reaction when we're adding bromic acid in.
You were just doing that because we don't really care about the
Bromine
spectators.
spectator, yeah.
Okay.
So I just left this big. Because we know HBr, when we have this aqueous, is actually H3O+ and Br-. And I was like, oh, Br- goes away, and it's just H3O+.
That's, okay.
Right, so I was just kind of putting that step together. But we can have the Br there. We just have to recognize that it's a spectator. And all that really matters is that we've got a proton donor and a proton acceptor. So we've got our proton donor, proton acceptor mediated by the H3O+ in water, and we form our HONH3+. Right, and then we can do this reaction now. We're at the equivalence point. How many millimoles of HONH2 do you have? What's the name of this? I know it's in the problem.
Oh, hydroxylamine?
Hydroxylamine. Okay, yeah, that makes sense, yeah.
7.2.
Millimoles?
Yes.
Okay, great.
You do that. You ask a question that makes you...
No, I just wanted the units. You just said 7.2, and I was like, that's either a lot of moles or it's millimoles.
You said how many millimoles do we
Oh,
have?
I did?
Yeah.
I'm tired today.
That's okay.
My 4 to 6 class is going to be rough today. And we're doing equivalence points, so we've got 7.2 millimoles here. We're going to have 0 there. We don't really care about that. That's going to be our start, our reaction, our excess. It's minus 7.2, minus 7.2, plus 7.2, all with our 1-to-1 ratios. Right? And we probably could have done this step in our head because it's the equivalence point.
Yeah, you multiply that.
Right, so there's our 7.2 millimoles of our hydroxyl ammonium.
This insert and this one.
I don't think that's the right thing to call that.
Hydroxylamine? No. Oh,
It's
okay.
hydroxylamine, it's a protonated hydroxylamine. I'm certain it probably has a special name, but I just don't know the special name. So at this point we say, okay, well that hydroxylamine, that conjugate weak acid, is going to have some equilibrium in water. Now, when I look at my options for the equilibriums I consider, I've got no hydroxylamine, I've got no leftover hydrobromic acid, I've only got the protonated hydroxylamine. So the equilibrium I have to consider is only going to be HONH3 plus H2O goes to HONH2 plus H3O plus. Where I've got, we got to be careful, where I've got zeros here to start. Approximate zeros there, and I got to figure out what they really are. Now, the mistake that I've seen at least 3 people make during office hours so far is they put the 7.2, this initial, like what do we put for our initial protonated hydroxylamine?
7.2 divided by the volume?
Which volume?
The
Total volume. Right, so total volume at this point is going to be the original 20 milliliters plus how much did we solve for that we needed to add?
My initial was 24 if you're using my numbers.
Oh, let's use your numbers, 24. And we added how much?
In the first part of the problem?
Yeah.
65.45.
That's gonna be 89.45. So I'm gonna need this 72 millimoles divided by 89.45 milliliters to get to my concentration. The mistakes I saw people make were they were just using the millimoles, they were using the original concentration, they were dividing by the volume of base they added rather than the total volume. Common mistakes, right? We need moles divided by total volume.
So I got 0.080 as the concentration.
0.08.
0.08. And then
Any other digits after that, or is it like 080?
it's a 0, yeah, 0.0804.
Okay, that's our molarity.
And then we have minus x, plus x, plus x.
Now we're just doing a nice table like we've always done.
The thing that stuck me though was we have to find Ka.
Yeah, the K, that's where
Oh,
yeah.
how do we find Ka?
You do the Kw over Kb.
Yeah.
That's what I got stuck on.
Oh yeah, that's another common
Because I
place,
just
right?
went all the way through and I was like, why am I getting it wrong?
And the KB we got in the KB was 1.8 times 10 to the negative
Yeah.
7.
Right, so this is Ka. This is another really common mistake. X squared over 0.0804. We got to make sure we use the Ka when we're set up for the Ka. We got to make sure we're using the Kb when we're set up for the Kb. So the other common place, whenever we're at equivalence point and we're flipping between, oh, we were doing a weak acid this whole time and now we're doing its conjugate base, or we were doing a weak base this whole time and now we're doing its conjugate acid. That's the place where we start to really miss that.
I'm just doubting this answer for sure.
Well, let's do some logical things. We have a weak acid in solution. Should your pH be high or low?
Low.
Low. Right, we're expecting a pH that's somewhere below 7, probably not crazy below 7. My hunch would say like 5-ish.
I got 4.15.
I got 4.17.
Yeah.
Is it right?
It's
Oh, good.
I'm never right.
You're
It's all-
right often. You just skip the parts where you're right and you go to find something else you can be wrong about.
Maybe. I need therapy.
I mean,
Uh,
eventually all of us do.
and remind me where we got our KB. Did you look that up on our?
Yeah,
okay,
it's on the
okay,
equation sheet.
Yeah.
On the equation sheet.
Okay. And we knew we were working with KB because at the very beginning, it's behaving like a
Over here.
base. It's accepting.
And then
Okay.
we didn't go to Ka
So that's-
for
okay.
D.
Yeah.
So there we go.
So
That's
number 10 will
9.
just repeat the same things for another problem.
Yeah, so number 10 is the same.
Okay.
Right, so number 10 has us do it. It's a little bit
You're
different. Let me
working
double
with the
check it.
conjugate acid. And so
Yeah.
you're working with, since you're in an acid, you have to find, like this is how it's.
Number 10 is the same thing except for you're going to have weak acid and its conjugate. You're going to have the weak base and its conjugate acid both present.
That's okay.
So yeah, same thing. Number 11. Number 11 is a little bit strange.
Wait, what's the
The K is like, it's 5.56.
So it just doesn't, weak acid and the
And then you
conjugate
just
base
looked
will be
up all the
present
The K.
Mhm.
in 10.
Yeah.
No, you have to stop.
Right,
it,
so
like,
10
you do the-
10 is going to be like the calculations we did last Wednesday.
You have to like find.
Oh yeah, that was.
Before the midterm. Everyone remembers what we did before the
So
midterm.
since
Yeah.
you
Oh, so to get
Oh,
X, okay, so
well, to get
Okay.
to get to X, you have to
find the K.
Oh,
first have
so
the
I-
K.
Yeah, I should have this arrow pointing the other way.
Are we gonna do 10 or 11 or?
We can.
X squared over your concentration.
We can do 10 and 11 right now, or we can come
Could
back to 10 and 11 in a little bit.
Could you do 12? Okay, so on 12, I'll show you my work.
Let me say one thing about 11.
Right.
11, the mistake that people make on 11 is, if I'm reading this correctly, number 11 is when you've added excess acid. Oh, someone did have a question about this one.
Yeah, let's do it.
So let's do number 11, but this is pretty much number 9 done. Number 10, exact same thing, except for you're going to have 2 numbers left over at your excess part instead of just 1. exactly like the problems we did Wednesday in class, except for it's a weak base instead of a weak acid. But since we still have our choice between equilibrium, we can still do the weak acid equilibrium. It's going to be fine. Number 11 is a little bit strange. Let's see, how much do I need to erase to do number 11?
For number 10,
Uh-huh.
I solved it by like looking at the midpoint. Is that like I first did since it's at half?
Oh, is it at the midpoint?
It doesn't explicitly say that, but it says what volume of HBr is needed to add half the number of moles of acid and as base, and so I like.
Oh, so it is the midpoint.
Yeah.
Yeah,
So
then
then
it's
I
just
just solved
pH equals pKa.
Okay.
That's
Yeah, I was
super easy.
like, wait.
That's way easier than I thought. So number 11? Or that's number 10?
That was 10. Number 11
10?
is
Super
after the
easy.
equivalence, so it's twice the number of moles.
So number 11 is the one that gets a little bit tricky. So number 11, how many moles of HBr are we putting in? Is it 14.4?
For number 11,
Yeah.
how many moles of what?
HBr are we putting in? And you can give me millimoles.
Oh. So what we do, say that again.
How many millimoles of HBr are we putting in number 11?
Well, how do I figure that out?
I don't know. I thought it was just told us, right?
No.
Consider the solution in question, 24 milliliters of 3 molar hydroxide with different, twice the number of moles. So you figure out, like, if we've got 7.2 millimoles, what volume do we need to put in twice the number of moles of HBr? So that's going to be, I'm just doubling my number of millimoles. I want 14.4 millimoles. So I'm just taking that 7.2 millimoles and doubling it. So we've got 14.4. Now here's the interesting thing about this. Whoa, that's a weird form. So we do minus 7.2 minus 7.2 plus 7.2. This becomes 7.2 millimoles. This becomes 0 millimoles. And our HBr is 7.2 millimoles left over. Right, we've got this excess amount of HBr in solution. So we say, hey, let's go ahead and do our equilibrium. Our equilibrium is now going to be where right, we don't actually need to do the equilibrium. Why not? If we've got 0,
Do you mean 7.2?
Oh, sorry.
No, just to be clear.
I put that in the wrong spot anyway. That should be 0. This is 7.7. 7.2, yes, I do mean 7.2. 7.2 divided by volume total. 7.2 divided by volume total. Great. I've got my conjugate acid. I've got my excess acid. And then I've got my 0, so I know it has to go towards the products for the equilibrium I have set up. Minus x plus x plus x. Approximately 7.2 divided by volume total. X. And approximately 7.2 divided by volume total. Does the amount of H plus from the protonated hydroxylamine matter for my total H3O plus?
Can you ask that question one more time?
Does the equilibrium of the protonated hydroxylamine, this thing donating protons, does it matter in my total amount of H3O plus at equilibrium? if I'm using the excess small approximation,
Does what matter one more time?
this thing donated, does this equilibrium matter?
Why wouldn't it matter?
You tell me. What cases would it matter? What cases wouldn't it matter? Let's do that thinking first. Think about this. There's already H plus in solution. What cases would it not matter?
There's no H plus in solution.
No, there's that's the opposite.
That's the opposite.
When there's only.
When there's only.
If there's okay, so if we think about this, is this a strong acid or a weak acid?
Weak.
It's weak acid. How much H plus is it going to put into solution?
Not much.
So does that not much matter? Depends, right? So the amount that this disassociates may or may not matter, depending on how well it disassociates versus how much is already present. If there's a lot of H3O plus already present, the disassociation isn't going to matter. Or if the disassociation is really, really, really tiny because it's got a very small Ka, the disassociation probably isn't going to matter. Right? So there's these cases where we can say, essentially, if X is small in our equilibrium, H3O plus is approximately the same. Right? The disassociation of this acid hasn't changed my H3O plus concentration in any measurable way. Now, is that a good approximation? Probably, usually has been. There's a few cases where it's not. I don't know the Ka for this, so I might be totally off, but since it was a weak base, I'm guessing the Ka for this is really small, like probably on the order of like 10 to the minus 10 or 11.
10.
Oh, 10 to the negative 5, that's not nearly as weak as I thought, but still.
Is it for the? Oh, I got
Oh, that was the
5.56
KB.
e to
Oh,
the
to
negative
the
8.
When did
Sorry.
you get
Negative
that?
8.
To solve the part
Previous
D,
problem.
For 9D, you had to get the Ka.
Got it. So we were together.
So with a Ka, what did we say, 5 point?
5.56 e to the negative 8.
With a Ka that's small, I'm probably not going to put much H plus into solution, which means my H3O plus is probably not going to change much from the equilibrium, which means I don't even need to do this equilibrium. I just wrote it down to show you we didn't need to do it, which really bothers my students in my 353 class. We spent like an hour doing something to show that it was 0.
Well, yes and no. That thing that you were telling us about earlier in class where you said, I'm doing this to show you that it all cancels out.
Yeah.
I did that 3 or 4 times, even though I knew, just
Yeah.
because I saw it and now I get it. So.
Yeah. No, and we're about to do, I'm about to do that again by Friday. I don't think we'll get to it on Wednesday, but maybe on Wednesday, but on Friday, we'll start using the Henderson-Hasselbalch equation. It's just more shortcuts. It's great. You don't like it? You don't even know what it is.
I do.
Dr. Retzik in her video used it.
Yeah.
Yeah.
Right.
Yeah.
So it's just doing math steps before us. It's doing less math to get the answer quicker, but if you don't know the chemistry going on, skipping the math can be a real headache.
So we're just doing this to help us like visualize what's
Yeah.
going on.
So I'm still not clear. We're still solving for A. We still haven't solved what volume of HBr.
Oh, I skipped that one.
Yeah, I'm so confused at where you are because I was like looking at A and trying to watch your work.
Oh yeah, no. I was way past that.
Yeah.
Sorry.
I've been.
So, since it said double the moles, I just doubled the moles and just kept working without solving for the volume.
Yeah.
What's the concentration of your base?
0.3.
So you're going to take that number of moles per liter. Oh, why can't I do math? You're going to do that divided by the concentration, and that's the volume. 14.0. 14.4 divided by 0.3. So you get 48 milliliters.
Yeah. Okay. Yeah, this
Right,
whole
but
time,
I
I
didn't-
didn't know you skipped that, and I've been watching all this going.
Now, that 48 is why I haven't evaluated this volume total yet, because I didn't have the 48, and I need the 48 to get the volume total.
I think, did you mean to say the molarity of our HBr?
Yeah.
Yeah, it's 0.11, not.
Oh,
point-
shoot,
yeah.
sorry.
So it's 144,
Oh, that's fine too.
but it's still saying it's incorrect.
For that one, since it's just asking for the volume of HBr, and we already know it from 10, and then, or from 9,
I
we've
got
got it,
130.9.
and then 10, I just divided by 2.
You said
So I just
0.11?
multiplied
14.4 divided by 0.1.
0.1? Or point?
So 0.11.
0.11. Throws your numbers off a little bit.
Let's see.
Okay.
It's still
We just
incorrect.
use most of the same stuff in the
What?
first question.
But you're now.
What volume of HBr is needed to add half the number of
Twice the
moles?
number of moles? What do you mean?
You're on number 10 instead of number 11. We're doing number 11.
Oh, sorry. So what volume of HBr?
Yeah, it'll never be right if you're doing the wrong question.
yeah.
Sorry about that.
See, I would sit with that for a while and go, what?
Yeah, well, you told me we could skip number 10.
That's-
and then
I
you
know.
didn't skip number
Yeah.
10.
And we didn't skip it, yeah.
Okay,
That's
so
it's the same.
So enter the formula for the first chemical species predominantly present after adding the volume of HBr in part A, that will determine the pH of the solution. So the formula for the first chemical species after adding HBr is going to be our conjugate acid.
sure.
And so,
What essentially what that question is asking is what's present at the initial step. When we're at this initial step, what's not 0? That's what those questions are asking.
HON H3 plus. It says that's wrong.
Changes what chemical species?
Oh, is it only asking for one?
Enter the formula of the first chemical species predominantly present after adding the volume of HBr in part A.
And you do that.
And I
by
entered in
doing
what
the
we got as our
stress
conjugate
state.
Oh.
The start reactants.
It's gonna be something, let me see how this is phrased. That will determine pH. Okay, so this part B is the conceptual work of what we were talking about while you were looking at something else.
B on number 11.
B on number 11.
Okay.
Right, so B on number 11. All this work I just did in green
Mm-hmm.
was to show you that this HONH3 plus doesn't actually matter.
Yeah.
Because we've got the X small approximation, so like, I didn't have to do this. The only thing that is going to really determine the pH is the H3O plus. Right, that equilibrium, sure, you could argue with me and you can say, no, that equilibrium definitely puts a little bit of H plus into solution. And I will say, yes, technically you're correct, but with a Ka like this, it's going to be like 0.0001%.
So it's not enough to change the pH, which is what the question's asking.
Exactly.
Okay.
So the only thing that really dominates the pH in this situation is the H3O plus from the excess HBr.
So then when we are calculating the pH from after this work that we've done,
We don't even need to do the stuff in green. We could have done it from the 7.2 millimoles divided by total volume. The excess HBr, I was pointing at the wrong spot. Right, because after we do the equilibrium, it's still about 7.2.
So
total volume is going to be
pH for
the milliliters that we figured out for part
I
A
would
and the initial
do
volume.
this thing then, but it's gonna be.
Okay, so that gives me my concentration,
What was your volume total?
this volume
130.9. So that gave me 0.0464 for my concentration.
Use the same.
So I'm getting to a point where I kind of forgot what we just
So
What
we're
we're
gonna
doing.
do
I calculated 7.2 divided by total volume.
Mm-hmm. That should get you concentration. That gets us a couple things. Right? There's two things that have that millimoles. There's going to be two concentrations. That's going to be our concentration of HO and H3 initially. That's going to be our concentration of H3O plus initially. And if you want, we can solve for X and we can show X is really, really small. Do you have a question?
No, kind of. I'm just trying to do my 11C, but
What's 11? Is 11C? What's the pH?
Yeah.
That's what we're working on right now.
Yeah, so I'm just trying to understand.
So you know how we just wrote, we figured out that in that green part, even though it wasn't really necessary to do all that, we figured out that the concentration of H3O plus is 7.2 approximately.
Divided by total volume.
Divided by total volume. We know the total volume because we calculated it in part A plus the initial.
So the concentration of.
Yeah.
So then we got the concentration.
So we can calculate here, we can calculate the concentration of H3O plus from HBr. I'm just going to do that real quick. The 138, the 7.2 divided by 138.
But so now we have a new volume of HBr. So do I?
In number 11?
What volume of HBr is needed to add twice the number of moles? Oh, never mind.
Right. So it's still that volume that we calculated from part
From
A or B.
Okay.
Right, and so I've got a concentration of 0.052 molarity for my H3O plus. And I could even say if I'm looking at my HO and H3 plus, it's also 0.052 molarity. Right, both of those things have the same molarity. Good on that part? Then we say, okay, do I need to, and is that the same number you got? Just make sure we're all on the same page. 0.052?
No, I got 0.0464.
You said 138. Is that, did I write this wrong? Is that 130 or 138?
Total volume for the work that you have up there is 130.9 plus 24.
Oh, yeah, I have a mistake here.
It's 154.9.
That's where my mistake is. 154.9 volume total,
Yeah.
which is the volume of base added plus the initial volume. That's going to give me 154.9
0.0464.
times 7.2.0465 if we're going to round it because it's 4648.
Okay.
But it should be close enough.
Right there, when you said we didn't need to do that second green part really because we saw that that equilibrium didn't matter much. How would we know if we had just stopped at that top bit? Where would we have looked to find our concentration of H3O plus?
26.
Hydrobromic acid?
Yeah.
Because it's essentially the same concentration, it dissociates completely.
Yep.
That's your fault.
What do I divide with?
Okay.
So are you trying to figure out your concentration?
Or bromic acid.
Yeah.
Let's get your total volume. So you've got,
Sorry, I don't know.
so you're going to do your 125.74 plus your 26. That'll be your total volume. And then we can take your millimoles of excess acid. You do the stoichiometry.
Where? What? Sorry.
So let's get your total volume first.
Yeah.
One thing at a time. So your total volume is 151.7. Let's write that down someplace.
This is my number 9.
Okay.
I'm just like.
What?
Oh, that's probably why
How am I
things are
doing?
going a little bit
Kind of
wonky.
okay.
Yeah, I haven't done.
Yeah, I
10
went through
yet.
the,
I was
You don't
I've
need
been
to
doing
do
the
10 to do
homework,
11.
and it's
Yeah.
like I keep getting them right, and I'm like,
So then.
don't fight it. But I'm so, he was explaining at the
Equals
beginning
your
of
total
office
volume.
hours at the beginning of this class is the,
Okay.
well, before we did
Now, so
anything,
that's your
he was
total
talking about
volume.
how the
You
first
also need to figure out what's
2
your
or 3
moles
homework
of
sets are like the
excess
hardest part of the whole class.
acid.
And after
So
that, you're kind of
that's why
cruising.
you, that's why
And
you're
so if you
getting
struggle with
mixed
stuff
up
at the
is 'cause you were
beginning,
looking at
like,
numbers
it's gonna
from
get
number
better.
9 when we were
Yeah.
doing
Which is
number
encouraging.
11. And they're really similar, but they're at different
Have you
points
watched
in the
lectures
titration
from
curve.
Dr. Retzek?
Yeah,
So
yeah, it helps.
In
I
textbooks.
write out
Yeah.
this stress table again.
Mhm.
Okay.
for a different volume, you've calculated your volume, you got your 125.74 new stress table, that's what's on the board there. Where at the end of the stress table, you're going to have excess hydrobromic acid and some produced conjugate acid. Now we get those into concentrations. You're going to have millimoles for those. We get them into concentrations by doing those millimoles divided by that total volume.
Okay,
Does that make
yeah,
sense?
that makes sense.
Okay. Now we're on the same page.
I'm just, yeah, trying to
So
catch up.
once we have, yeah, sorry, I didn't know you were looking at number 9 still. So once we have our millimoles at the end of the reaction, and we divide by our total volume to get our concentrations, we can ask this question of, did I need to bother doing the equilibrium table?
No.
And the answer is no. And we say, okay, well, why did I bother doing it? It was to show that the answer was no. Right, so when I look at this, I say I've got some amount of this protonated hydroxylamine, and then I've got some H3O plus from an HBr disassociating. These two things, I do go through and do my equilibrium table. I'm going to have that minus x plus x plus x. And I'm going to use x small approximation. And you notice if I use the x small approximation, my concentration at equilibrium is just this value from up here. And it turns out anytime you have excess strong component, whether it's strong base or strong acid, the excess strong is always going to dominate like this. Almost always, like always for our class. Now, why did I just backtrack on that? So if you remember the titration curves that I like to draw, we have this sort of thing. I'll draw it for the weak base because we're doing the weak base one, which is just flipped over. We calculate, I don't have us calculate that whole area. I just have us calculate the equivalence point. That's because all that space I marked in orange where like our approximations don't work, in that area, like leading down towards here, x still matters for a little while. There's this range where x still matters before you're in like a real excess area. And in this area, you have to solve a quadratic for the equilibrium of water in low concentrations of excess acid. We could do that. It's not something I would ask you to do in class very often, maybe like 1 or 2 problems just to show you could do it. But never on an exam, never on a quiz. Right? We're dealing with areas down here where the excess small approximation is valid again. Remember, any place where you see a bit of curvature, that's because there's some quadratic being solved. That's why it's got that kind of like parabolic curve to it, because it's got some x squared term to it. So we'll always stick to the flat bits, buffer region, excess region, initial point, equivalence point. Those are the places where we will look. Places where our approximations are pretty good. So we could have looked at this right as we did our stoichiometry and said, oh, obviously we've got so much excess acid, I can just take the negative log of that concentration and that's going to be my pH. The reason I took 20 minutes to do that was because it's not obvious to us yet. Right? We're just figuring this out. And so walking through the process is part of how we figure that out. That's 11.
Okay.
Okay?
Yeah.
12, 13, 14, and number 9 on 4.2. Let's see 12, 13, 14 real quick. Okay. 12. 12 I think is not too bad. 13 is a little bit strange. 14 I think is okay. So we can go through these pretty quick.
Do you need, you probably know all this, never mind.
What?
The chemical formula for morphine?
No, I don't. I don't even need it to do the problem. But what is it? C17, H19, NO3?
Mm-hmm.
Okay. So, okay if I erase all this? Okay. Okay, so we go on and we say, okay, let's look at number, are we doing, did I say 12?
Yeah.
So number 12.
Oh, okay.
So number 12, we're going to say, I'm just going to call it a base B, right? That's where I'm going to shortcut my morphine thing. I know it's a base in water. I'm going to say it's morphine. I'm going to say, in this case, B is morphine. It's got the C17H19N, was it NO2?
NO3.
NO3. I'm really curious about the structure now, because anytime I use a shortcut, I like to look at the structure.
That's not great.
You're gonna look at it in NOCAM.
Okay.
I'm never going to.
I'm not going to draw that, but so it's got a bridged ring, which is why I'm not going to try to draw it. If it was just rings, I would draw it, but I'm really bad at drawing bridged rings. So it's got some structure to it. I'm just going to treat it like this, where I'm going to form HB plus and OH minus. And the problem, let's before I get too ahead of myself, does someone want to read the problem so I don't get lost?
A 0.15 molar solution of morphine has a pH of 10.5. What's its Kp?
So high pH, we know it's acting like a base. It's also asking for the Kb. If I look at this, I can do this like so couple things. It's just saying morphine and water behaving like a base. There's no acid being added. There's no strong acid. There's no strong base. This is just going to be equilibrium. So I'm going to have that 0.15. I'm going to start with zeros here. I'm going to have minus x. Why do I keep switching colors? I wanted that in green to make it so it was clear from my shortcut. So I'm going to have minus x plus x plus x. That's going to give me approximately, we'll just go approximately 0.15 x and x. And at this point, we're looking stuck. Because what I'm going to get is I'm going to get Kb is equal to x squared over 0.15. But I don't have Kb and I don't have x.
Wait,
pH.
why don't we just use the pH to get the OH concentration?
That's what we do. So it turns out we do have x. Was that what you were going to say too?
No, I was just wondering, because we can use that assumption that Kb equals x squared over the initial. Can we use that for bases as well as acids? Because I know we only.
Well, I mean, I just did it through the equilibrium table.
Okay.
Right? And it turns out, yeah, for weak bases, weak acids, they come out the same. It's just Kb and OH instead of Ka and H3O+. So our X's meaning has changed between the two, which is what a lot of people miss.
Yeah, it's H3O versus OH. Gotcha.
So as long as we keep track of all those things, yeah, it's the same every time. If you noticed, when we're at the equivalence point, same thing, right? Whenever we just have a weak base in solution, that's what we do. Whenever we have a weak acid in solution, almost the same thing. So it turns out we can do this pH to POH to OH minus concentration.
3.162 times 10 to the -4.
Which means we know what X is.
I did that and it told me my answer was wrong. I'll show you my work.
Show me your work.
So real quick, ignore my equation here. I just sort of forgot that it was acting like a base. That's the correct equation.
No problem.
But look, I did exactly what you said. I put Kb.
Well, let's check a couple things.
The only thing I did different was I didn't assume that it was 0.15. I kept the x and then I plugged the 3.162.
Oh,
that.
So because we know x, we don't assume it's
Yeah.
Come
Right, we
on,
know what
Jay.
X is, so we don't need to do the approximation. We can just do that. Yeah, we don't need to. 3.1677 should have been good enough still.
That's what I thought, but I normally just, if I know x, I don't assume.
Yeah, we should, if we know what X is, we shouldn't assume.
If we do that sort of thing on like a quiz, is that fine?
You'll be fine.
I'm really curious. So I want to check something real quick. 3.16.
I wonder how sensitive the answers are.
It's always very sensitive to me.
That may be frustrating.
What answer do you get without x is small?
I just erased it. Hang on. 3.16 times 10 to the minus 4 squared divided by 0.15. 6.66 times 10 to the 1.
I still,
Your numbers might be slightly different. Did you get it right?
I got it right when I didn't assume, and I basically got the same answer if I did the x is small part.
Which problem is this?
It's number 12.
6.66 times 10
Did any of your decimals change?
times 10.
The only thing that changed,
Minus.
I
Maybe.
got 6.68 10 to the negative 7, and then without the x is small, I got 6.6.
Oh, I think I know what I did.
times 6. So it's like pretty close.
Wow, that's weird. It should allow for 3% error, and so it
Oh,
seems like
got
this rounding error, like this idea of x is small, should be within the 3% allowance.
It
Yeah.
is. The reason it was initially incorrect, I referenced back because I didn't input this x value squared.
Oh, yeah,
But as
yeah,
soon as
yeah.
I fixed it, that's a
Yeah, because it's like 6.66 versus
It's really
6.65 or something like that.
yeah.
And so you, I was kind of surprised that it didn't work with
Yeah.
it or without it. It should work with either way, because I
Yeah,
double
it worked
checked in the code. This is the x is small is less than the 3% error, and I had a 3% allowance on it. So normally, there I think there was one problem with like an acid that was kind of strong, where if you did the x is small approximation, it created like a 7% error, and I didn't allow that. And that was like on homework 2.1, something like that.
That might I got stuck on one, and I realized I was doing x
Yeah.
small, and then I had to fix
And the
it,
reason
so.
that one stood out to me as like, oh, it's gonna be you can't do x is small, was because the pH was really low, so the x was kind of a big number.
Yeah.
And so I was like, it doesn't seem like the x value is like 0.015, and that's like 0.015. That's like pretty close to the concentration. I think that's gonna matter.
Yeah, I think I remember that one. That's
Yeah.
why now I just always plug it in for x.
Well, it's like
Okay.
if you have it.
Yeah, might as well.
So that was number 12. I just lose. Oh, there it is.
6.66. That's a terrible pH.
Random numbers. Okay, number 13. The phrasing gets a lot of people because they don't read the textbook, so they don't look at percent disassociation, right? And again, number 13 is going to be really similar to what we just did, where it's a weak acid though, so we're going to get to this situation where Ka equals x squared divided by 0.15 minus x, right? I could set up the equilibrium table, but it's just this thing in water, but it just says percent disassociation, right? And so the thing here is just the language of what percent disassociation means. And it's got to either be telling us something about Ka, or something about X, or something about the initial concentration. Let me make sure I'm setting this up correctly. Right, so we're given initial concentration. It's not 1.5, sorry, it's 0.128 for me. Now, what do you think disassociation is going to relate to, Ka or X?
X.
Yeah. So our percent disassociation, if I have, so let's think about this. If 0.128, if I 100% disassociated, what would my X value be?
0.128.
If it 10% disassociated, how much would it be?
10% of that?
0.0128.
I don't know.
Now, if it is 1.54% disassociated, right? It's really just percent disassociation is another way of just telling us what X is.
So I had randomly 1.54% disassociated, so I do my 128 times 0.00154. Sorry, 0.0154. Too many zeros there.
0.00197.
Because you got a different number?
Same numbers.
Oh, that's what the value ends up being.
Yes.
Okay.
0.0019. Well, 0.002.
So we plug that in for our x. Solve.
Wait, so the 0.128 is your molarity.
0.128 was my random molarity. So it's molarity times percent disassociation equals x. So I do my molarity times my percent disassociation, which is 1.5% disassociated. Technically it's disassociation divided by 100. And that gets me my x value. Right, and that makes some amount of sense because x is how much did it fall apart in solution.
And so then the denominator would be that
What?
new number minus our x.
Yeah.
Okay.
Which is still going to be about 0.1. Oh, no, sorry. This is our x. Our concentration minus our
Yeah,
x.
yeah,
Yeah.
sorry. That's what I meant.
New number could mean a lot of different things, but
Yeah,
I think we're on the
the
same page.
given molarity minus
Perfect,
our
yes,
x. Okay,
yes.
Sorry about that.
No, you're all good. I didn't sleep enough this weekend.
You drink too much?
No,
You graded too much?
graded too much. I've got one more page of my 353 exam. I'm done grading your exams. I just have to total up all the numbers.
Don't total mine. Just leave it as nothing.
You probably did better than you think.
Don't think so.
Okay. Well, that still tracks with what I just said.
Yeah, but this is clicking, which is great.
Good.
So moving forward, right?
Moving forward.
I have tutoring. Thank you so much.
Okay, you bet. I'll see you later.
Good job. So, if this is my percent dissociation, that's my given molarity. I'm
Okay.
at
So I think that gets us through most of these. That's 13.
4 times.
Yeah.
14 I can do real quick as well.
Okay, so times
Dr. Urker,
Yeah.
0.
can I talk to you for like maybe 5 seconds?
Yeah, I think did you send me an email? Yeah, let's talk real quick. I'm going to pause this and we'll step outside real quick.